Okay, good morning, everybody. Morning. We're going to finish today with chapter 10. We're going to do 2 more examples of elastic energy. Good morning. Okay, so let us remind us what is the elastic energy. Okay, we have a new term in the total mechanical energy. Good morning. So we do have the kinetic energy. We have the potential energy associated with the gravitational force, and then the potential energy associated with the elastic force, which is the elastic energy. Each one of these terms is the following. This term here appears when we move up and down. Okay, gravity, of course, it acts all the time, but when the height is constant, then this term will cancel out. Let's say the energy at the initial point and the energy at the final point, the potential energy due to the gravitational force is going to be the same. So unless that we move up and down, this term will not matter much. And then we have another term, which is 1/2 kx squared. So notice that here we have 2 different coordinates. One is the measurement of the elasticity of the spring, the elongation, whether we elongate or we compress. And the other one is whether we are going up and down. So whether we are going up and down or left, right, we're going to use each one of these terms. So if we attach a spring, immediately we have this x squared term here, the potential energy, the elastic potential energy. If we do not have a spring, but we move up and down, then we have the gravity acting, and then we need to consider the potential energy of a gravity force. And in general, okay, we're going to see a problem where we have to use both of them. So chapter 6, okay, this was chapter 6. This is chapter 10. But in either way, in chapter 10, we're going to see problems where we have a spring moving in the vertical direction, and then this will be a change in x and a change in h. Then we need to actually define, we're going to see that we will define 2 coordinate systems, really, okay, because this x is measured from a given point, and then h is measured from another point that we could choose. X we cannot choose, really, where we measure. Okay, so here actually it's important to, well, in principle, let's say yes, we could still choose, different points, but here we always choose x from the unstrained situation. H we measure from the bottom sometimes, so sometimes from the top if we are dropping something from a height. Okay, we have some freedom to choose the value of h and less freedom to choose the value of x. Okay, so then let's see some examples. We're going to do example number 9 from the book. Okay, let's show the example here. A falling ball. Oh, can you see? Let me see. I lost it. Okay, yeah, you're right. Okay, hope that you see the book. Okay, a falling ball on a vertical spring. So we have a 0.2 kilograms ball attached to the vertical spring, and it is as given in the figure. The spring constant of the spring is 28 newtons per meter, the ball supported initially so that the spring is neither stretched nor compressed. Okay, that's actually important to consider here. And then it's released from rest. Okay, we have a nice situation here where we have to combine both of them. Actually, yeah, we go directly to a combination of both elasticity and gravitation. In the absence of air resistance, this is actually always the same because, as I said before, we never consider friction nor the viscosity of the air. So then all these problems are energy conservation, at least in this chapter. Okay, in chapter 6, we saw some cases where the energy was not conserved, and then you have to include also the energy dissipation. Here, there is no dissipation of energy. The question is, how far does the ball fall before being brought to a momentary stop by the spring? Exactly, thank you. So yeah, so then you figure out what it is, what the problem is doing here, right? So we have we release the ball by gravity will go down, but then there is a restorative force, which is the force of the spring that is against gravity. So the force of the spring is actually increasing, right? From here to here. Here we have zero force. And while we zero force, I mean the spring, okay? Because here the spring is unstrained, is not being compressed nor extended. However, here as we release the ball, there is a elastic force going up. And this will actually slow down the motion. Okay, it will actually slow down until the velocity is zero, and then the velocity will reverse, and then this will start to oscillate. So that's the problem that we want to solve. And all right, so then this is interesting because we have to really use actually the two terms. Okay, so actually last time we did a problem where we used only the elasticity because the spring was moving horizontally. Now this spring is moving vertically. Okay, so then let's repeat here the problem, and then what is most important here is to put the coordinate system which is consistent with the problem. You have some freedom again to choose a coordinate system, but let's see the simplest one. So you always start with the unstrained coordinate. Okay, this is unstrained position. Okay, so why this is important? Because here you're going to measure the position that is x equals 0. So this is the x equals 0 position. Okay, anything above or below this. Okay, and then here actually you could even have some freedom. Let's say you could put positive x here and negative x here. Okay, it is like we have this coordinate system, something like that. Okay, positive x, negative x. But now we put it like that. Okay, this x, it doesn't mean that it has to be in the x direction. In the horizontal direction. Okay, so x is the direction of the elongation of the spring. Okay, so this is not actually the initial point, because the initial point is when we attach a ball here. We attach a mass. Here there is a mass which is 0.02. No, so 0.2 kilos. Now, as soon as I attach the mass, so here there is nothing, right? So this is the really unstrained position where I do not attach the mass to the string. As soon as I attach the mass, then of course this spring is going to move down, but it's not moving down because we are holding it. We're holding it with either with your hand or with the table or whatever, right? So you hold it in place. Okay. So now this is now the initial position. So let's call this position A. This is really the initial position. We are holding it there. And then we say, okay, we release it. at a later time. And then, of course, it's going to go down like that. And it's going to go until some position. Okay, that in principle, I do not know what is this position. Okay, and let's call this position B. Okay, and then that's actually what we want to find out. Okay, so then that's all what is given. Okay, so what would you do here? Think about it and let me know. You want to find, in principle, okay, let's set up the problem. Let's repeat it. Find, let's see how it is stated in the book. So find how far does it go. When it is stretched, gravity is working on the ball. Yeah, exactly. So gravity is working all the time, right? Gravity is always, you know, right here. Right here we have the weight. Yeah, right here. So gravity is always acting here, right? All the way, you know, gravity is acting here. So what is the force of elasticity at this point at A? So what is Fe at A? Yeah, this guy is 0. Great. This guy is 0 because we are starting from the point. Okay, so which principle are you going to use here? What is the main equation that you will be using? Exactly. EB, okay, EA equal to EB. So that's the main equation, okay, because energy is conserved. Okay, we say there is no resistance, nothing strange, and then that's the one that give you the variables that you want, right? So then, in order to calculate the energy, okay, if you go back here to the definition, you need to know where you're measuring H, and you need to know where you're measuring X. Both, you know, you need to know both. So then, the variables that you want to calculate here is one is the XB. Okay, you want to know how far does it go. Okay, how far does it go from where? Okay, you are measuring X equal to 0 here. So you want to measure X. Okay, let's call it X, not XF, but XB. Okay. At the same time, you're measuring the height. Okay, and the height, you could actually use another coordinate system. Okay, if you put here, because usually we put H equal to 0 in the bottom. Okay, so let's use that coordinate system for the H. Okay, so the X you always measure from the unstrained situation. The height also you could put it there, but let's say here I'm actually following the book, okay, that measures H equal to 0 here at the bottom, and therefore what you are looking for is HB. This is the one that you're looking for in this problem. Now, if you look at HB and XB, this is exactly the same. Okay, so HB, the height that we measure from the bottom, even in this coordinate system, they are the same with even with the sign, and this is equal to XB. Okay, so then we're gonna find only one variable. That's what you want to find, HB. So then you write down this full equation, okay, using this coordinate system. In principle, let us write it in general. Let me go to the next page. So we have 1/2 mVA squared plus Okay, no problem. So if you cannot participate in polls, that's okay. So MGHA plus 1/2 KXA square equal to the same thing in the BB, okay, in the point B, MGHB plus 1/2 KXB square. Okay, so then as usual, that's all the time the same. So you put A, energy at the point A equal to the energy at the point B. Okay, question of XB equal to HB. Okay, I mean, it is pretty much the same variable. So we are actually looking at this, this position here, the position between A and B. Okay, the point is that we have two terms in the energy. One is measured from the unstrained position, and the other one we are measuring from the bottom. So kind of we have two coordinate systems here. That's what you have to do in these problems. You choose the coordinate system of the energy, and you choose also the potential energy, gravitation, and then you choose the coordinate system of the elastic potential energy. So you have this freedom. The problem is not going to depend on the coordinate system. Is this always the case with height and position? Yes, pretty much yes. So every time that you have a problem with height and position, yes, you do. This coordinate system is always fixed, okay? So this one here, the red one, always come from the position of unstrained, and you measure x equals 0 there. Otherwise, this equation is not correct, okay? These equations assume, this equation here, 1/2 kx squared, assume that when x is equal to 0, you don't have any energy, you don't have any force. And then this is the place where the string is unstrained. There is no elongation, again, no elongation, no compression. So this one here, you should keep it like that. The other one, since it is linear, then you have more freedom to move it, to put it whatever you want. So here, just to fix ideas, let's always do the same. Okay, so you put it the h equals 0 at the bottom. This is the maximum elongation, and x equal to 0 at the unstrained position. And then you go and solve the problem with that coordinate system. So again, if you don't use this coordinate system, the problem can be solved anyway, but I guess that this is the easiest one. Remember that we can always pick an easy coordinate system so that yeah, we have so that we can solve the problem in the easiest possible way. Okay. Any questions? Nope. Okay. All right. Okay, so now what do you do next? Yeah, I start canceling. Okay, yeah, canceling variables and then putting everything to 0, right? So all the variables that are 0. So which variables are 0 here? Okay, what is the velocity at the position A? Velocity at position A and velocity at position B. Exactly, they're both 0, 0, 0, and 0 here. Okay, so then that's great because, okay, we start canceling. BA is gone, BB is gone. Okay, what else do we have 0 here? Okay, the XA, yeah, the X, exactly. The X, but be careful, only at position A, right? Only at position A, there is 0 because that's exactly where we put the 0. Okay, so then this guy also cancel out. What about position B? Position B, not, okay, because that's actually the one that we want to calculate. Okay, this is non-zero. Is there any other 0 here? Yes, there is an extra 0. So how much is the value? Yeah, HA. Exactly. Well, here actually is, look, I did a little mistake here, because this is not HB. That should be, if we are consistent, okay, that should be HA. Okay. This is HA. So this is the position, right? So it's this position here. So from the bottom, okay, to the initial position, that's what we call H. Exactly. HB is 0. Very here, the HB, which is the final position, okay, that's the one that is 0. Is that everybody okay with that? Okay, so here I did a little mistake. Okay, it was not HB that we are looking for. Let's say yeah, it's not HB what we are looking for. So HB in this particular coordinate system is directly 0. The one that we are looking for is HA. Okay, the H is confusing. Yeah. Why HB is 0? Yeah, so, okay, so let's put this guy here, HB 0, and then we cancel out. Okay, let me just rewrite this equation, and then we investigate why HB is 0. So eventually I get mg HA equal to 1/2 K XB equal to 0. So that's the equation that we got from here. So let us review why, going back here, why the 1H, AB, whatever it is, one is 0 and the other one is not. Okay, so let's actually review what's happened with X. Okay, X is clear. So first you choose the coordinate system. Once you choose the coordinate system, then the position should be super clear. My coordinate system of X is 0 here at the initial position. So then X initial is 0 here, right? X initial is 0 because I'm starting from here and then I am ending right here. Now, for the case of H, the coordinate system is different. You see H is positive going up, and then is negative here going down. This is H negative. And then the H0 is right here. Okay, so that's the H0. So then if you come here and you look at it, HB is 0, clearly, because that's where I put the 0 in H. Doesn't really matter that XB is non-zero. Okay, this doesn't really matter. And then HA, where is HA? You go all the way here, and then you measure from here to here. So then HA is this distance here, and this is the one that is non-zero. Okay, and then what we want to find is HA equal to XB. So this is how you actually connect the two coordinate systems, because at the end, the position is just one. Whether it is 0 or not, it depends on the coordinate system, and at the end, you will have only one variable. Okay, and that's the one that is HA. So this is what you want to find. You want to find HA, and that's actually what it is asking in the problem. Okay, so in the book they call it H final and H0. So how will that how will we know to put H equal to 0 there? Well, again, so you first define the coordinate system. Okay, when the coordinate system is defined, and that's what we did here, everything should be clear. A and B should be clear. Okay, everything comes from the definition of the coordinate system. So we are assuming that the point of longest elongation is where H starts and it is 0. Exactly. The point of longest elongation is exactly where it starts to come back, right? So first I release it. I release the ball, reaches the longest, the largest elongation. And then it comes back. And at that point is where I put h equals 0. Because I want to know what's happened when the ball comes back. Okay, from the height 0. Usually you put the height 0 at the bottom. Okay. So now we are looking at for this. So what it means is that GHA, because here I have two variables, right? I cannot really solve this equation. I have only one equation, therefore I need one variable. Then when I get one variable when I put that the XB is equal to HA. So then here I have HA squared. And only now I can actually, finish this problem. You put it like that. Cancel, cancel. You put the 2. This is 2 mg divided by k, and this is the one that you want to find out here, HA. Okay, so you put here the values, 2 times mass, 0.2 kilograms times 9.8 meters per second square, and then you divide by 28. 28, you could put, this is actually newtons per meter, but newton is kilograms, meter divided by second square, and then here you have a meter. This is actually over meter. So then this guy cancel, kilo, kilo cancel, and then you see that you have everything in meters. Okay, so then HA equals 2.14 meters, and that's your answer. Okay. All right. Second block gone for the semester. We start a new block here. All right. Any questions about this? Is this clear? Right. So then these are the type of issues, problems that you're going to see in the exam. Okay. So again, if you're missing all these lectures, you might be in trouble. Okay, so any questions about this? Everything is clear? Okay. All right, then let's move on. All right, good. Okay, so let me do an extra final problem. Need to practice, but the explanation makes sense. Okay, good. Okay, let's do another problem which involves a little bit of more calculation. Let's do a problem in the homework. Let's do the homework problem 1029. Okay, so let me check. Yeah, here is the problem. Okay, so here we have a 2 kilogram object hanging from the end of a vertical spring. Okay, the problem is the same as before. We have to deal with the height and with the position. The spring constant is 50 newtons per meter. The object is pulled 0.2 downward and released from rest. Complete the following table by calculating the kinetic energy, gravitational energy, elastic energy, total mechanical energy. The vertical position h indicates distances above the point of release, where h is equal to 0. All right. Okay, so we have the following situation. This has an extra, an extra issue that we didn't have in the previous problem. Okay, so we always start with the spring with nothing on it. Okay, and then we put that in red, so then you remember that we are measuring x equals 0 from here. So all the distances for the elongation, okay, all the distance from the elongation will be measured from here. So this is the unstrained position. Okay, so here actually, if we read the problem carefully, it says, the object is hanging from the, we put now an object, okay, and then it's hanging from the end of a vertical spring, meaning that we already put here the object, we attach it to the spring, and then it's hanging there without the table. Okay, this is actually without the table. So this is the initial position now. So this is the initial position. It's different initial position. It's different from before. Okay, before we have the mass attached, and then we hold it there with your hand or with the table, something like that, and then you remove the hand, and then the ball is going to fall down, and then it's going to start to oscillate because of the spring. Now it's actually different. Okay, this initial position is where the ball is hanging. Ball is hanging at rest there, without anything. Okay, without any, without any table there holding the wall. So then this is now a new position, XC. Let's call it XC. And this is something that, in principle, we need to calculate because it's not, it's not given here. So this is our initial. Well, that's not even the initial position. Okay. So let's see what's happened there. Now, the object is pulled 0.2 meters downward and released from rest. Okay. This is not let's call this the pre-initial condition. The real initial condition is when we move from here downward 0.2 meters, and then the ball is right here, meaning that we are actually really elongating this guy. Okay, we are elongated all the way up to here. This is now the real initial position. Okay, this is the initial position, let's call it A. And this is the initial position. Okay, there are three actually, three positions that you have to consider. Okay, first the unstrained situation. This is not even given in the problem, but anyway, you have to put it there because that's from where we measure the x equals 0. So notice that the x, okay, we measure all the time from here. So far, I didn't even bother to say what's happened with the height. Okay, the height didn't even appear here. Okay, so then first we measure, we measure everything from x equals 0 to the pre-initial position where the ball is at rest. Then what you do, you take this ball and then you move it down up to this position, and that's the point A. Okay, and this is the real initial position. So what is the velocity at this point? Yeah, the velocity is 0. Exactly. So the velocity is 0 because we are not measuring. Okay, we are releasing from rest. Okay, so then that's exactly. Will A be the initial position because it is the longest stretch? Not really. That's a good question. This one here is not the position that you No, that's not the longest. Okay, this actually is where you start to release. So imagine that here, so here is actually hanging there. This is also with velocity 0. This position also has velocity 0. The point is that you take the ball here, you move it down all the way up to here. Okay, take it with your hands, you stretch it, and then you release it. So what is going to do the ball is going to move up and down. Okay, but then it's going to keep going down, right? It's gonna pass this position here. So we do not know here which one is the initial position or not. The initial velocity of an elongated string is 0. Yes, the answer is yes. If you release it with 0 velocities, right? So this is you elongate it, you release it, and then definitely that initial position is 0 because you are releasing it with 0 velocity, right? Because you're releasing the ball. Okay, so the object is pulled 0.2 downward and then released from rest. That's actually what they say. You know, they are pulled downward and released from rest. Okay, and this implies that the initial velocity is 0. Okay, can you describe what it will be if they get exactly? So you could actually, okay, so you elongate it, and suppose that, okay, you give it a push. So you, rather than release it and then start it from 0, you know, you give some momentum. Okay, so you could put some momentum here in the positive direction, and then this VA will be some velocity. Okay, you could give some velocity to the ball. You could give some velocity down as well, right? So you will push it a little bit down. So then here actually is clear because it is actually released you know, it is released from rest. Okay, so then the vertical position. Okay, so here actually this is the crucial point. Okay, they say the vertical position is measured from the point of release. Okay, be careful that here is different from what we did here. Here the release point was right here, and we measure the initial position from the bottom. This is the maximum elongation. This is not the maximum elongation, but in principle we do not know where is maximum elongation here. And then in the problem it says the vertical position h indicates, this is actually the problem, distances above the point of release. The point of release. What it means is that h equals 0 is right here at the point of release. It's not the elongation, it's just the point of release. So then we measure h positive right here, and then h negative right here. Okay, positive and then negative from h equals 0. Okay, so then the question is, you know, they want to calculate, here in this problem is calculate the kinetic energy, the potential energy G, the potential energy elastic at different points. Okay, at the point h equals 0, which is right here. Okay, this h equals 0. At the point h equal to 0.2, which is right here, h equal to 0.2. And at the point h equal to 0.4. Okay, we don't even know where is 0.4. Okay, because we don't know what is the value of xc in principle, but let's see that h equal to 0.4 is right here. Okay, we do not know because I know where it is from here, but I do not know what is the value of xc. So I still do not know what is the relationship between the x coordinate and the h coordinate. Okay, is this relatively clear? Okay, so what is this ball? Okay, what is this ball is gonna do, right? So then let's put it. This is the A. So we want to know what's happened when the HA is equal to 0. Let's call this B, and let's call this C. Okay, so this ball here is going up, something like that. Okay, with the given velocity. Okay, BB. And then here, actually, we do not know whether it is going up or down. I mean, the problem is not, in principle, up to this point. But okay, let us assume that it's still going up with the velocity that we call VC. Okay, so these are all the things that we need to calculate. Although what we need to calculate is the kinetic energy. Okay, so we need to calculate the kinetic energy, the potential, elastic, and gravitational. Okay, so let us start at point A. Okay, are you using C twice? A, B, C? Where is XC here? Okay, that's not a good. Okay, let's call this X naught. Okay, that actually is actually better. Let's call it this the X equilibrium. Okay, because the initial position is at rest, and this is at rest at equilibrium. Okay, why this is at equilibrium, and this is not. Okay, here is not at equilibrium. Right, so this one is at equilibrium, but this is not. Here I'm not doing anything, so I'm just taking the ball and leave it there. I'm not applying any force, any external force, and nothing, and it will remain there forever. So this is literally a force, a position at the equilibrium. What it means is that at this particular point, the sum of the forces will be equal to 0. That's the reason that this part here of the problem, okay, the first part, is kind of not connected to the other one. Okay, it's not connected to this. Okay, is the release point considered the same as equilibrium? Not really. The release point, okay, this is not a, I mean, in a sense, okay, it's a tricky question. It is at equilibrium because I'm holding, right? Holding it meaning that I am applying an extra force there. So if I consider the force that I am applying, the weight, and the restorative elastic force, yeah, all these things is at equilibrium. But when I release it, okay, then the ball is not at equilibrium anymore. And in fact, it will start to go up because the weight is smaller than the restorative force. Okay, so these are, I mean, there's little things here and there that require some thinking. Okay, we want to calculate the position at position A. Okay, everything. Okay, there is one that is easy to calculate. So what is the kinetic energy at position A? Yeah, this is exactly 0. Okay, that's 0 because we start with velocity 0, right? So that's easy because the velocity is actually 0. Now, if I want to calculate the potential energy, gravitational, P, E, G at position A, what would that be? Okay, let me do survey to see how many people are out there. Survey. Let's see, multiple choice. Calculate P, E, G sub A. Okay, 0, smaller than 0, or larger than 0. Question. Okay, keep going. Okay, some people are saying positive, other people are saying negative, other people are saying 0. More or less, well, it's actually interesting. Same number of people are saying 0 or positive, and then out of that, half of them are saying negative. It is an interesting number that we get. Honestly, I'm not sure. Yeah, isn't it 0 BCH0 exactly? So because HA, yeah. Okay, we got the response there already in the chat. All right. I'm not sure if you could change the answer. Okay, so then all the time, right? So you go to the definition. Okay, thank you very much for your response. Yeah, we got 31, 0, 15 positive, and then negative roughly 10. So, you know, half and half between correct and incorrect. So the correct answer is actually 0. Let's see why. So you just go to the definition, M, G, and then here you have to put the HA. Okay, how much is HA now? You go and then you look at the coordinate system. That's the reason we spend 10 minutes just putting the red line here, the green line here. Okay, these are the two lines that you want to do in this problem. Green and the red, and measure everything from here. Okay, do it even with two colors because these two coordinate systems are different. Okay, you have the H coordinate system and the X coordinate system, and these two guys are different. And in fact, I brought one guy here to make it yellow when it is really important. So if you like color coordination, hopefully you will like this marker, yellow. Okay, so this is a whoa yellow color here. Don't miss that. Okay, don't miss these guys. These are the guys that are given. Ah, that's nice. I like it. Okay, this and this, first thing you do. If you do this correctly, everything else is kind of relatively trivial because it's just a matter of coming here and say, okay, how much is the value of H at A? 0. Then this guy is actually 0, right? Because HA is equal to 0, and that's what we put right here. Another yellow guy here, so then you are now seeing the point. Okay, that's it. Okay, we got these two easy guys, 0 and 0. Okay, and that's actually how we choose the coordinate system in a sense that makes our our calculation easy. So 0 and 0, you don't need to calculate anything. All right. Okay, now we have a little bit more complication here. P E G. No, sorry. P E E. Okay. P E E. Sorry that there are so many subindices here. P E E at the point A. Okay. Potential energy elastic. P E E at the point A, and that's what we want to calculate. And that's a little bit more complicated. So we know that this is 1/2 by definition, okay, 1/2 K, and let's call it here what X you put here, X sub A square. Okay, now let's do another survey. Polling, multiple choice. Is X sub A equal to 0.2? None of the above. Question. XA 0. XA 0.2. None of the above. A lot of people are saying 0. XA. 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 Where do you measure X? You don't measure X from the H from here. You measure it from here. Okay, X0 is all the way right here. Now we are down. Okay, X cannot be 0. That's okay. The majority of people are saying that XA is 0, and this cannot be. It's not 0. Definitely it's not 0 because the position here in the coordinate system of H is 0, but not in the coordinate system of X. Okay. All right, you stop there. Okay, I mean, yeah, okay, there you go. There you go. That's the answer. Okay, so I hope that should be clear. So XA, okay, if you look at the XA, what is that XA? Right. Okay. So just look at the coordinate system. So which one is XA? Let's put it here. I didn't even put it XA, what it is. Okay, but if you look at this, it comes all the way from here. This is XA. Okay, so definitely it's not 0. So if you say here that it's 0, come back, review the problem very carefully, because that's a big mistake to say that XA is equal to 0, because clearly it's not, because the ball is down there. Here it's actually, positive, let's say. Well, we didn't even say here X. Okay, so this guy here, so X going down is positive, and X going up is negative. Okay, so that's the same coordinate system that we had before. Positive, negative, H positive and negative. Notice that there are even different signs. Okay, the height is usually positive when we go up. The elongation X is positive when it is an elongation, and is negative when it is a compression. Okay, so then again, here there was a big red flag again. Okay, so many people say 0. That's a typical question in a multiple choice, and then, or even if it is not a question in the multiple choice, if you do the incorrect answer there, if you do this and you put 0 here, then yeah, you will be in trouble, right, for the remaining part of the problem. This is something that is fundamental. Okay, so then if you look at there, clearly XA is what we call XE, which is the equilibrium position, plus 0.2 meters. Okay, that's actually what it is given in the problem. The initial position, it is explicitly said, is obtained after we let the ball hang in there at equilibrium, and then we additionally elongated 0.2 meters. So some people also say XA is 0.2 meters. Why this is not? Why XA is not 0.2 meters? I cannot actually ask you questions, in the polling, because polling is just yes or no, or multiple choice. But okay, let me give you the answer. Okay, so this is, XA is not measured from the equilibrium. It is measured from the point where there is nothing attached in the string, because XA does not depend, let's say, this initial position, okay, has to be measured from the point when there is nothing on the spring. The spring is just hanging there. There was something in the chat. As far away from 0.2. Yeah, because x0 is as far away from more than exactly. I'm not sure this answer is correct, but okay. As long as Ranaya, as long as you understand, that's fine. Okay, so this is important. Okay, so then what we need to calculate now is xe, right? This is not given in the problem. Okay, xe is not given in the problem. So how do we get xe? Any hints here looking at the problem? We need to calculate xe, because there is no way to calculate xa unless they know xe, the equilibrium position. Any hint? So what's happened at xe? What do we say? The system is at equilibrium. It's not at equilibrium here, okay, because here I'm holding it. But right here is at equilibrium. So at xe, I have equilibrium, what does it mean? Is that all the forces, energy, no. That's actually a good answer, Rainuk. I mean, it's a wrong answer, but it's a good mistake, let's say, because it is reasonable. So the energy is actually zero. The energy is actually not really zero, okay, at this point, because there is already some elongation. Okay, there are some energy associated with this. There is even potential energy of gravity. I mean, energy is really not zero. So what it is actually zero is the sum of the forces equal to zero. Okay, one thing is to be at equilibrium, the other thing is to be at rest, holding it with the force. Okay, so in a sense, at rest is always at equilibrium, but you have to add the force that you are actually using to hold the particular mass at this particular point. Here, nobody's holding anything. So then if you use the equilibrium equation or the free body diagram, okay, what you have here is there is a force down, which is the weight, and there is a force up, which is the elastic force. And these two things, they have to be equal and opposite. So Fe plus the weight is actually zero, which means that Fe in vectors, right, is minus the weight. Okay, so that's the equilibrium situation, only at this particular point. And that's the one that you can use now to calculate what is the value of Xe. Now it's gonna be tricky because, okay, I have, let me put it back. Okay, right here, because we need to see the drawing. Okay, that's the most important one. So then let me repeat at Xe what is going on. Okay, we have the force, the elastic force, right? The elastic force at the point Fe at the point, Xe, let's call it like this. Sorry for the notation. Okay, we know that this is K times the elongation. The elongation at this point is what we call the equilibrium position, Xe. Do we know the mass? Yes. Mass, exactly. We need to know the mass. Good. The mass is 2 kilos. Not only that, we know K. Okay, K we know 50 newtons per meter. Okay, otherwise this equation will not be, it will be possible to solve, exactly. So here we really need these guys. So the weight, okay, is the mass times G. Okay, these two has to be equal. Okay, if you want to really put it correctly, okay, so we have a force, Fe going down, and then the weight going down. Sorry, the force going up, and then the weight going down. Okay, so then when we calculate the sum of the forces, it is the Fe minus W, and all this is equal to zero. All this is equal to zero because the acceleration is equal to zero, right? Here is kind of coming back to chapter 4. Okay, there is not even energy involved here. So what implies here is that Fe, again, at this particular position, right? This is only for this particular position, is equal to the weight, and then you say, well, K times Xe is equal to the mass times gravity, and then you get that Xe here is mg divided by K. Okay, mass 2 kilos times 9.8 meters per second square divided by K, which is 50. Let's do the units. Newton, meter, second square, divided by another meter here. Meter, cancel, this, cancel this, cancel. The meter goes up. Okay, yeah, Mohammed, yeah, one second, let me finish this. Okay, Xe, okay, we get, which is 0.39 meters. Okay, we calculated now the first quantity here. Yeah, can you move up the paper? Yeah, okay, sorry. Okay. Okay, so I just put 2 kilos. Let me redo this. Okay, 2 kilos times 9.8 divided by 50. Yeah, 0.39. Okay, there was a question there. Why I just said before, yeah, right here, right? That F is equal to minus W here, okay? And then in this equation, I got F equal to W. Okay, be careful here because this actually is as a vector. Okay, Fe as a vector is minus W. That's the reason I put here as a vector. Here is already the absolute value, meaning that I put the negative here. Okay, in other words, the weight is negative. With the negative here, then you get an Fe that is positive. Okay, so that's be careful over there. Okay, so how much is XA now? Let me do another survey to see if you are following. Okay, here you have to, everybody should get this answer, right? This answer should be, you're following there, everybody should get this. 0.2 in meters, right? At choice 0.39, 0.59. Okay. Now we should obtain 100% correct answer here. Okay, that's correct. Okay, so that shouldn't be, although we get a lot of people who do not answer. Yes, keep going, because, okay, go. Many people do not answer. That's kind of bad. So give me an answer anyway. So no answer means you are not in, you are in Blackboard, but you're not following. You're not even listening, which is even worse. Okay, keep going. We just calculated XE. Now I'm asking, what is the value of XA? Now, let's go back here, right? So what is XA? Keep going. We have still 24 people who didn't answer. K units are Newton per, yeah, exactly. So K, okay, 50 here. See, 50 newtons per second. And that's what I put here. So Newton per meter. You see 50 Newton, okay, this part here is what I call, okay, what we call Newton, right? Kilograms, meters, second square, divided by the mass. This is also important, okay, so then always check that you get the correct units. Okay, I'm not sure why you're so slow responding, so let's finish this and let's do a little bit of a break here. Okay, again, we are having a lot of people who said 0.39. That's not correct. A lot of people who say 0.2. That's not correct. A lot of people who still say 0, because we already told you that XA is non-zero. So that was the previous question. So still we got 4 people who said XA equal to 0. So XA cannot be 0.2. So we say that XA is from here to here. Okay, let me stop. And then there are a lot of people that are not responding. So I'm not sure where are these people. Okay, so XA definitely is not 0. XA is not 0.39, right? So this guy XE is 0.39. Okay, XE is 0.39 from here to here. So then XA is 0.59. XA is 0.59 meters. Okay, it's 0.2 plus 0.39. 59 meters. Okay, that's the next answer. So we got one answer. The next thing to calculate was XA. Okay, so let's finish this. Okay, so we see that there actually, let's say these are questions that I mean, I was expecting like 100% correct answer here, because I mean, I just gave you that XA is XE plus 0.2, right? So then if we just calculated XE 1 second before, you just need to add 0.2 to this guy. So it was not a question that you will require thinking about the problem, or it's just the math. Okay, so just doing the math will give you the answer. So, in all these problems, there are always two things. One is the physics, the conceptual problem. You have to look at the problem. The other thing is the math. This was a math question. So saying adding two numbers, 0.2 to 0.39. Okay, so everybody should have said here the correct answer. Let me see the chat. Okay, no problem. Yeah, if there is a mistake, no problem. Yeah, exactly, Andrew. That's correct what you say. It will take 50 newtons to stretch 1 meter. Exactly. That's exactly the definition of K. All right, now let's do this and then let's have a break. All right, so then now we have, what are we doing here? Okay, we go back and then we wanted to calculate PE at the point, well, PEE, okay, potential, let me see, you can see this, all right, here, PEE, okay, we wanted to calculate this guy here, PEE, potential energy elastic at the point A, and that's what we're calculating here, is 1/2 K, and here you get XA, that's the reason we are calculating XA. You need to get the position, the correct position first, 0.59, and then you go and do the calculation, which is 1/2 50 Newton. Let's do it again, Newton in the proper units, in the fundamental units. So then you don't miss. Okay, so you actually, yeah, the potential energy. We're going to calculate potential energy. I will actually leave it in newtons. Okay, let's leave it in newtons. Okay, because in this particular case, we're calculating the potential energy. And the potential energy is given in what? In joules, right? The potential energy is an energy. This is given in joules, and then joules is Newton times meter. Okay, so then it's better here to leave it in meters, because in meters and newtons, okay, because yeah, that's what we want to get. 59, and then this is actually square. So let me write it down, because it's, I got a little bit, yeah, deviating from what it should be. So then let's leave it in Newton per meter, and then times 0.59 square times meter square. Okay, and then you see that this meter cancel with this. And then we have newtons per meter, which is joules, and that's very good, because that's exactly what you want to get. Okay, 1/2 50 times 0.59 square, all this in joules, and that's, how much is that? 8 point PEA is equal to 8.76 joules. All right, so we ended up with the potential energy, okay, at the point A. Okay, I will give you a break, but okay, so let's see what we calculated. We calculated the kinetic energy at point A. Then we calculated the potential energy of gravity at point A. And now here I calculated the potential energy of the elastic spring at the point A. Question for you to think. Question. Okay, what is the total energy at the point A? Okay, let me give you a poll, and then we'll return in 5 minutes. Polling. EA. Okay, that's the total energy now. EA. First answer is 8.76, negative 8.76. I do not know. Well, let's say, oh, I need to calculate it. Let's say, oh, I don't know. Okay. No, I don't know. I mean, cannot say, let's say. Cannot say meaning that with whatever we calculated, we cannot calculate this guy. Okay, so we need to calculate, we need to do more calculations. Cannot say. Okay, I give you with this poll and then we will be back in 5 minutes. Okay, welcome back. Let's see. Yeah, it's 8.76, right? The question is, okay, EA. Okay, so the other two are, of course, 0 and 8.76. That's the EA. So EA is 8.76 joules. All right. Yet, okay, 4 people say 0. 36, 8.76. Great. Sorry, yeah, 37 now. 4 people say negative, minus 8.76. And then 5 people say, I cannot say. So still we cannot get the 100% right. Okay, and then no response, 19. Meaning that 19 people are not even here. All right, so 5. Okay, let's finish the problem now. So we got that the total energy, EA, is 8.76 joules, and then the potential energy elastic at A is equal to the same, 8.76. Okay, of course, that meaning that the other two are 0. Now, let's go back to the problem, where it is. Okay, here. Okay, the next point is calculate everything at the point B. Okay, let's do this. Let's see if we could finish that. Calculate all of it, right? The potential, well, let's start with the kinetic energy at the point B. Potential energy gravity at the point B. Potential energy elastic at the point B. And then also the total energy at the point B. Okay, so we want to get these numbers right. All this at B. Okay, what can you calculate here and what can you not? Which number is the easiest one to calculate out of 1, 2, 3, and 4? Which one is the easiest? 1? What does it mean 1? I don't know. 1. So I have 1, 2, 3, 4 quantities. Yeah, P, E, G, B. Okay, I mean easiest, or it's a little bit yeah, easiest. Yes, easiest means that you don't need to do any calculation. No, you don't need to do anything. So just put the number. Which one you know directly the number without doing any calculation. Do you know KEB? Coming back, we are right here, okay? Yeah, PE, no, is not 0. Is XE same as XB? No, XB is not XE, Ranaya. Good question, answer is no. Now, what do I know about all these numbers? EB, exactly. Reshmin said the correct answer. This is the guy that you can calculate easily. Exactly, Oscar, good. EB, okay, we know that EB is actually equal to EA. Okay, and in fact it's equal to EC. Okay, in fact it's equal to the total energy. This is energy conservation. Energy conservation. Okay, so this number here has to be equal to 8.76 joule. In fact, we are going to calculate this at the point C. Okay, later on, we are going to calculate it at the point C. So then at the point C, what is the total energy again? What is going to be the total energy at the point C? What is this number here? Exactly, 8.76 joules. And in fact, we already calculated that at the point A. Now, okay, let me remove this guy here because we are doing like a little table, and the B or the A, whatever, right? This is actually right here. Okay, I'm recalculating everything. Let's say not recalculating, but putting back what we know. Okay, we calculated that this is 876 joules. We calculated that PE at the point A is 8.76 joules, and therefore this is 0 and this is 0. Okay, the sum of the first three columns has to be equal to the sum of the last column. Not the sum, so the sum of the first three columns has to be equal to the last column. All right, so then let us now calculate at the point B. Okay, at point B, what is going on? At point B, what is going on? So let us start with P, E, E, and B. The spring is rebounding. Exactly, the spring is rebounding. So we have 1/2 K, and we do have to calculate this XB square. Okay, this is by definition. So let's come back here and see what is XB. Okay, actually somebody said there, okay, somebody gave me the correct answer. I said that it was not correct, but it is correct. So what is XB? XB is position here. This is the XB. Okay, exactly. Ranai, I sorry, I say that it was wrong because there was no reason for this to be the same. Okay, that's good. So then you went ahead and then you did the calculation. There's no reason for this to be the same, but actually the fact that we are saying that, okay, HB is 0.2, okay, the distance from here to here is 0.2, and this is HB. Okay, then it means that exactly XB is equal to 0.39. Exactly. XB here is equal to XE. That was a very good point. You catch it, and that's great. So then XB is 0.39. Okay, 0.39 meters. Okay, so then you calculated this PEB equal to 1/2 50 newtons per meters times 0.39 meters square. Okay, you do this calculation. Sorry if I didn't show this correctly. So you do this calculation. What you get is 384 joules, and this guy is the guy that you put here, 3.84 joules. Okay. Now let's calculate the P potential energy gravitational at point B. Again, go back here. Okay, the definition. Mass, gravity times HB. When you come here, how much is the value of HB? Point two. Okay, exactly. That's actually given in the problem. Okay, so then this is mass. What is the mass here? Mass. We have K and mass. What was the mass? 2. Great. 2 kilos times 9.8 meters per second square times HB, which is 0.2 meters. How much is that? 3.92 joules. Okay, we get here 3.92 joules. 92 plus 3.84 equal minus 8.76. Now, question. How much is kinetic energy at the point B? Exactly. So now let's try to look at the definition. Okay, 1/2 mvv squared. Do we have the velocity at the point B? Yes or not? Do we know the velocity at point B? No. Okay, we do not know it exactly. We do not know this velocity. Good. No. Okay, so then, but we know that the sum of all these guys, they are equal to the total energy. Okay, that's the reason, in a sense, we first calculated the total energy before. Okay, at the point A, we were able to calculate the total energy because we calculated the potential energy, elastic, and that's the total energy because the other two are 0. Exactly. We add these two, okay, this. Okay, so how do we calculate this? We do not use the velocity because we do not have it, but we know that KEB plus potential energy gravity at B plus potential energy elastic at B equal to the total elastic energy, the total mechanical energy, which is at B or at A, doesn't really matter. This is the same all the time at 8.76 joules. Okay, so then KEB is equal to 8.76 joules minus the other two, minus 3.92 minus 3.84, and it just happened that this is just 1 joule by, a coincidence. Okay, just 1 joule, and this completes the the calculation at B. Okay, all right, so we have 2 extra minutes. Let me do quickly the calculation at C. Calculation at point C. Calculation at point C, we need to come back here. At C, at the point C, we have the potential energy elastic at C. 1/2 K xc squared. So how much is xc? Let's come back here. This is actually a little bit tricky. Okay, because now, let's see, is C the not really. Well, that's again a question that no, it's not gonna be. Okay, let's see. I never. Yeah. Okay. It is the maximum height, but in principle, I cannot tell in advance, let's say, but by some miracle, we're gonna see why it is. Okay, but in principle, I mean, it's very good that you guess it. Great. I mean, that was a great. Sorry, this is HC. But it's not that easy to guess it. But okay, let's see what it is. Here it's not so clear, how to calculate it. So let's say what it is, whether it's maximum height or not, but at the end it's gonna be. Okay, so what is this value of xc? So yeah, of xc. So we have 0.4 from here, okay, because that's the question. They're asking, okay, what is the total energy, okay, all the different energies at the point C. The point C is 0.4 starting from the bottom. Okay, so then xc is this little guy here. It will be the total 0.59. Okay, the total initial height, which is 0.59 meters minus 0.4 meters. Okay, that's the height that we are looking for. Sorry, not the height, right? This is the elongation. So this is this elongation. Let's put it here in red. Sorry that it's getting a little bit crowded. Okay, but okay, so this guy here, from this point to here, that's what we call xc, and this is 0.19 meters. Okay, with that xc, then we come here and calculate 1/2 50 newtons per meters times 0.19 meters square, and then we get whatever it is, the value of this. Can do the calculation. Yeah, 0.19, 1/2, 0.92 joules. Okay. Now, what is the PEG at the point C? Now we have MGHC, and HC 2 kilos times 9.8 meters per second times this is actually given. Okay, this is the 0.4 meters. Yeah, 0.4 meters. Great. And that's give us 7.84 joule. And that's the PEG at Z. Now, what if we sum these two? 7 point plus 0.92. What do you get? So let's put it here in the plot. So the gravitational is point in the table 0.84 joules. The other one is 0.92 joules. Now what's happened with KEB? Sorry, KEC. How much is that? How much is this guy now? Black screen. Hello? Can you hear me? Oh, you cannot see.
We can hear you. You can't see what's on your screen.
Oh, you cannot see my screen? Okay, let me double check. 1 second, I'll be back. Okay, we are finishing up anyway. Yeah, KE is 0, exactly. Share camera. Can you see it now?
No.
No? You cannot see? Okay, that's funny.
Yeah, sometimes Blackboard does that.
You really?
Yeah.
Okay. Well,
Yeah,
we were just... Yeah, so say it again, sorry?
I mean, we just need to refresh, but then it's already the end of the lecture. So
Yeah, okay, it's already the end of the lecture. Okay, now the answer is KEC is equal to 0, and this you will figure out. Okay, why? So what it means is that, yeah, literally at the point C, then that's the maximum elongation from the point of release. Okay, that's it's not the maximum elongation, the maximum height from the point of release. That's the point where the kinetic energy is all the way to 0. And then what it means is that it's going to, this guy, yeah, literally, is going to oscillate between, yeah, it's going to oscillate with the amplitude, or 2 times the amplitude of 0.4. Exactly. All right. Okay, so that's all for today. We went over a few minutes. Yeah. Do you have any question? Okay, if you refresh and if you want to see the final answer, okay, what we put here is the 0 right here. Because why? Because this guy, PEG plus PEE, okay, elastic plus gravitational, is exactly the total energy. So then there is no more kinetic energy at this point 4, and that's the point where the ball starts to return and come back. Okay, I guess there is one extra question over there. You can tell me. Yeah,
Prophet, quick question. This is Oscar. I'm not sure if you go back to the first page, when we set up where X positive and X negative and H plus and H minus were, like, I guess my question is like, ¿qué pasaría? Like, what would happen if we had switched that? Like, if we had put X positive going down, or
okay,
X positive going up. I'm sorry.
Yeah. Okay. Yeah. Good. I mean, it's a good question. Nothing will happen if you switch. I'm not sure if you're seeing my screen now.
Yeah.
Yeah. Okay. Good. So let's say you want to say, okay, X will be negative down.
Yes.
Okay, and X positive up. Okay. So we have to be careful. Yes, because let's say the definition of the force assume that an elongation is positive, let's say. When you are elongating, it is positive for the definition of the force. Now, for the definition of the energy, since this is actually x squared, right, doesn't really matter if you switch positive or negative. So it's a little bit tricky. I mean, I would say like, you know, choose it in this way. So positive when you have elongation for x, negative when you have compression for X. Although if you do not do this, and if you do another coordinate system, and if you are very careful, if you know really what you are doing, you will get the same result. Okay, but you will need to know, exactly what you are doing, because the force actually will actually change the sign, and then you may get into trouble, downstream.
Okay, I was just making sure. I was just curious what would happen. But
Yeah.
elongation
All right.
when you're pulling, take it as positive. Okay.
Exactly. I mean, in a sense, yeah, all the laws of physics are independent on the coordinate system. That's actually relativity, which we are gonna you're gonna see in physics 204. Actually, it should be totally independent on the coordinate system. So whatever you choose, you should get the same result. But if you choose the coordinate system that is not the normal one, then you have to do a little bit more work. That's the only thing. All right.
Okay.
Great.
Thanks.
No problem. Yeah, you're welcome. Okay, so there are no more questions.
Hey,
Yeah,
Professor,
see
I
you.
actually have one question.
Yeah, sure.
In our labs, we're talking about problems that are very similar to what we just went over in class, except in those cases, energy is not conserved. And that's kind of throwing me for a loop a little bit, and I'm just finding it a little bit harder to think about. And so I'm curious if you have any thoughts or tips on how to start thinking about that.
Yes.
Okay.
Yeah. Okay. Yeah. I mean, it's a good question. So, so when you say energy is not conserved, you mean you actually calculate the velocity, the position, blah blah blah, and then you sum up, and then the energy is not the same here, here, and here, something like that.
Yeah.
Exactly.
Like
And by
energy is
how
being
much?
lost to heat, essentially.
Exactly. Some energy is lost. Okay. By how much is not conserved? Let's say the question is when you start at the point B or at the point A, and then you keep going. So do you have an estimation of how much do you lose of energy, or do you remember?
I would. Let me see.
Say small or large. Let's say.
I would say it's pretty large. The body that's on the spring stops moving fairly quickly.
Okay. Yeah, then you lose all the energy. Okay, you lose everything. Okay, what are you doing there? You are actually hanging up and down, or on a surface, or
up and down?
Up and down. Okay. I mean, typically, if you have a spring, you just elongate it. I mean, it will take a while, right? So I guess I don't know. It's a very stiff spring or something that is not really ideal. But typically, when if you leave it there for 2-3 minutes, perhaps, or 5-10 minutes, eventually, the spring will go to rest, right? And then pretty much there you lose you are losing the energy. Now, this is in reality, it always happens, right? In reality, you will never have this perfect conservation of energy, never.
Yeah.
Because there is always friction, and here we are neglecting friction with the air, and the spring also may have some dissipation. It's not perfectly elastic, and then this thing will never happen. Now, at the same time, we are actually looking at a very small time scale, right? So I'm just releasing the spring. And then I'm just looking at just a few, even a microsecond later, because this is very fast. So then at this scale, the energy, even if you measure in the experiment, the energy will be the same pretty much. Now, if you let it, go up and down, eventually, it will dissipate. So all the systems are actually dissipatives, and then that's pretty much the answer to your question, which if you go into the book, let me see the book. There is an entire chapter on that, which is dissipative. Damped harmonic motion. Okay.
Oh, awesome. Okay, this is page
300. Is the sorry?
Page 300 or so, chapter 10.
Yeah, 300. Yeah, exactly. 300. That's exactly. So you see that the oscillations. Okay, the oscillations are the red one is perfect. Okay, conservation of energy. The other ones are all damped. Okay, so they go to zero eventually. You will lose the energy. So that's actually what is going on in your experiment.
All right. Thank you so much. And I hope you have a great weekend.
Okay, you too. Thank you so much.
Don't forget to stop recording.
Yeah, we stopped the recording here.